Simple electric heaters are really cheap to buy. For more money you'll even find Wi-Fi enabled smart devices. But there's the usual downside of them only working with proprietary apps. Even worse, they'll connect to the manufacturer's cloud and you're at their mercy to keep the service running. With a bit of tinkering though, we can make even the cheapest device smart and easily controllable by Home Assistant with no cloud at all. But there are more advantages than just ditching the cloud. I'll show you later. So let's dive right in. In general, turning electricity into heat is pretty darn expensive here in Germany. You'll pay around 35 cents per kilowatt hour compared to natural gas at around 9 cents. It's also pretty inefficient without a heat pump. But we recently added solar panels to our roof, and when the sky is clear they produce a lot of electricity, even in fall and winter. The main reason they produce less power overall in the colder half of the year are the shorter days and the denser cloud coverage. In any case, it's still pretty cold outside, and even on cloudy days there's usually at least a bit of power left to spare. Our central heating still runs on natural gas, so every kilowatt hour saved is a net benefit for the environment. To test my idea, a friend lent me one of the heaters he had used up until recently. It's Wi-Fi enabled, but it only runs with the Tuya cloud and app. Home Assistant already has a Tuya integration, so adding the heater was quick and easy. Turning it on and off is very reliable, but that's already about it. See, the heater has two modes, Eco and Comfort, which result in 1 and 2 kilowatts of power draw respectively. But the way the Tuya integration works, I can only set heat in Home Assistant. I can change the mode using the app, but the heater itself randomly decides to switch back to Eco whenever it pleases, even though I've set the desired temperature to 50 degrees C, which it can never reach anyway. The core idea of turning it on and off at a moment's notice worked very well though. Especially on days with intermittent cloud cover, solar power output can fluctuate by several kilowatts within just a few seconds. Since those heaters aren't much more than oversized toasters, they can take frequent switching pretty well. Like very strong incandescent light bulbs minus the light. For my purpose, the cheapest of them all should be good enough. They're pretty much guaranteed to be made in China, but since they're rebranded and sold by a German company with multiple million euros in revenue, they should be safe nonetheless. The power consumption can be set to 3 different levels: 750, 1250 and 2000 watts. They have 2 separate heating circuits, and the maximum setting works by activating both of them at once. I watched a few teardown videos to get a feeling for what's inside and if there are any surprises. They are really simple on the inside though, so modding them should be easy. Through the magic of bulk discount, I bought not 1 but 4 of them, which brought the price down to a measly 20 euros per unit. 3 of which I already put into service using smart Zigbee wall plugs, while I opened the last one to see what's inside and to come up with a plan how to wire up an ESP32. I got the variant featuring a fan, since it literally costs just €1 more. The fan works fine, but the way it's wired up is pretty annoying for the way I want to control the heater. We'll get to that later. I was really surprised. The insides look rock solid. They're using flame retardant glass fiber insulated silicone wires to connect everything, and the heating element has not 1 but 2 safety fuses. A self-resetting type and a permanent one in case things go horribly wrong. The way they work is basically cooling the heating element by drawing in cold air from the bottom. The hot air moves up rapidly, drawing in more cold air, just like a chimney. One way to break this concept and trip the fuse is using the heater without its plastic feet. I learned that from a video featuring a guy with an Eastern European accent where he showed how he just welds the fuse shut. Well, that's one way to fix it, literally, but back to the guts of the device. The power cable comes in at the bottom and ground is connected directly to the metal casing. Neutral is split up using some kind of wire nut to connect both the switches and the heating element. The only reason the switches need a neutral connection is they have little lights in them. They're only switching the live wire though. The unit has 3 switches, 1 for the fan and 2 for the weak and strong heating circuit. The live wire itself is switched by a simple thermostat. The lowest position will switch off live entirely, while higher settings will disconnect it at certain temperatures. At which temperatures, you ask? That's yours to guess. The manual doesn't give the slightest hint, and due to manufacturing tolerances, they might as well behave a little differently on each unit. Doesn't really matter for my case though, I'll leave them at maximum and control the rest via Home Assistant. Speaking of which, I still need a controller to manage the switching. There are a ton of different boards on AliExpress, so I made a short list of features I'd like to have. I need 2 relays for controlling the 2 heating circuits. Ideally the beefier 30 amp variety. I love to over-engineer things. Plus you can't trust the specs of Chinese knockoffs, so a safety margin of 50% is never a bad idea. Preferably it'll feature an ESP8266 since it's cheaper than an ESP32 and more than good enough to switch to relays. 230 volt mains power in is a must, so I don't need any additional power supply. Of course I could just wire different modules together, but I wanted to have everything nice and tidy without having to come up with my own circuit board. As with most things in life, you can only choose 2 of the 3 at best, so I had to make compromises. All the ESP8266 based boards I found run on DC only. The boards featuring the beefier 30 amp relays are DC only as well. If I wanted to run on mains voltage, I had to resort to the 10 amp rated relays. The controller being an ESP32 is not a big deal, just a waste of a lot of GPIO pins.
What is my purpose?
You switch 2 relays.
Oh my god.
As for the relays, they should be fine as well, since the maximum current of the strong heater is about 5.5 amps, so there's still plenty of headroom. I just couldn't find any tests of how much current they'll actually take before they break. On some Chinese parts, the numbers are just plainly made up, but those relays are everywhere, so I'll hope for the best. And besides, I'll be doing temperature checks anyway, just to be sure. The board itself was pretty inexpensive, less than 8 euros per piece. Okay, quick intervention from future me. I checked the most common signs of a knockoff, and one of them is blurry prints on the parts. I have some, hopefully original, relays from the same manufacturer lying around, and their print looks way better. It's hard to tell on camera, but easy to spot in person. I'm still not too worried about them failing though, since relays usually fail in the open position. And it's alternating current, which doesn't keep connections shut electromagnetically the same way DC does. There's also the thermostat as well as the 2 fuses shutting the power off if necessary. One annoying thing I didn't anticipate is that the fan will run permanently when switched on, regardless of the heating settings. So as long as the thermostat doesn't cut power entirely, it will run, even if both heating elements are off. That wasn't on my bingo card when I bought them, so the plan so far is to leave the fan out entirely and maybe come up with a solution later. The ESP32 has plenty of GPIO pins after all. In order to control the heating elements, I need to add a parallel wiring path to the existing switches. I wanted the unit to still work by manually turning on the switches in addition to the controller. For that, I bought identical wires with the same color scheme to ensure fire protection. I was a bit unsure which cross-section size I need. All doubts vanished anyway when I saw the power plug itself only has a cross-section of 0.75 square millimeters. That's about 18 American wire gauge. The wire I bought has a bit less than 17 AWG. For regular PVC insulated wire, that's enough for 10 amps, and high temperature wire can take even more amps, since the copper core really doesn't care about temperature as much as the insulation does. I thought of a few different variants on how to connect the controller to the heater. I could just cut some wires and solder another one in between. I've got these heat shrinks which have some low melting point solder inside. They're oddly satisfying to watch, but I was a bit worried about the low melting point of the solder. And besides, the existing cables are pretty short, so it's hard to solder anything in between. I was also thinking of Vago connectors. They're rated for continuous use at up to 80 degrees C. Apart from the heating element itself, which can reach around 300 degrees C, the area where the controls reside seems to stay below 80 degrees. There's already a wire nut anyway, so why not replace it with some German high-tech? But that also would have involved cutting wires. So I decided to just make my own Y adapters using cable shoes, just like the manufacturer already does on the switches. As a software developer, I just prefer modular options and backwards compatibility. The first test looked promising. I was able to slip the whole cross-section of 2 wires twisted together into the cable shoe. For the insulation to fit as well, I needed to remove the fiberglass wrap. No big deal, since they're still neatly isolated. The female part of the plugs needed a bit of extra tightening, since my shoes are a bit thinner than the ones on the switches. The contact area is what matters most anyway, and they have plenty. And for good measure and additional safety, I also added some heat shrink. I only used 70 mm of wire for the adapter itself and it looks a bit tight, but since they're under no mechanical stress, I'm not worried too much. The bending radius is still very reasonable. Before I moved on, I needed to design the case. I still had no idea how long the final wires for the controller needed to be. I didn't want to waste material, plus I had to make 4 identical sets, so I might as well get the necessary length straight from the start. For my test adapter, I just kept the whole spool of wire connected to cut it later. The plan was to route everything through these fins on the side. They didn't seem to do any particular cooling. There was also no feelable airflow, and besides that, the fan is sucking its air from the other direction. Nevertheless, I planned on not blocking them entirely. The case for the controller should have a bit of space beneath it. Another thing I realized at this point is that I needed to distribute the live wire to at least 3 connections. 2 for the relay's inputs and another one for the controller's power supply. Make that 4 if I ever decide to switch the fan as well. So there's a place for a good old Vago connector after all. What the case will look like is still very vague at this point. It'll probably be a rectangle of some kind, and it needs feet to keep some distance from the case itself. I started by measuring the distance of the holes in the circuit board and sketching them out. They're exactly the right size for M3 screws. I'm using the 6mm long version I still have plenty of from my Arduino DIY cat laser toy build. Link in the description in case you're interested. Next I sketched out holes for the feet. I made them hexagon shaped so they can't spin. Since the board has only 3 screw holes, I added some supports beneath it to prevent it from bending, some of which I later needed to remove again. I also needed 4 holes to screw the lid on later. The position of these holes needed to be selected carefully in order to not interfere with the screw terminals of the circuit board. Since I don't need the normally closed connection of the relay, the hole can be placed there. I also added a slot to route through all the wires. The controller also gets some air vents. I don't think they're really necessary, but in my opinion it makes everything look more professional. The first prototype worked pretty well already. I deliberately printed it in PLA since it's easy to handle and I still have some really cheap rolls here. The final version will be made from ABS for heat resistance. Only the feet touching the metal casing did I print in ABS right from the start. Otherwise they'd be guaranteed to melt almost instantly. I haven't found any markings on which material they are using for their stock plastic parts, but they feel like ABS to me. The internal plastic spacers are certainly made of some composite material from how they feel and because they're touching the heating element directly. For the cables, I thought long and hard about adding a strain relief, but ultimately decided against the extra effort since it's literally impossible to yank on those cables without pliers. You can certainly yank out the controller case if you put in enough force, but in a real-world scenario, those heaters aren't moved around, especially not while they're plugged in. With the prototype case printed, I needed to drill 4 holes into the sheet metal of the heater. I'm using screws I already had lying around, which aren't of the self-tapping variety. While attaching the case, I noticed a lucky coincidence with the case feet. I primarily designed them to be separate parts, so I don't need support material for the bottom of the case. But this also allows them to comply with the slight curvature of the heater casing. What a happy little accident. While I tried to figure out how to route the wires inside the case, I noticed that using the same mains voltage source for the heater relays and the controller has one big downside. Whenever the heater reaches the set temperature of the thermostat, it will shut off all power. That also means the controller has no power anymore and the relays turn off. But the heating elements definitely need to be attached to the thermostat for additional safety and to not heat the house to ludicrously high temperatures. The most reasonable way for me to solve this was adding another cable grabbing power directly from the connector of the wall outlet cable. This also means instead of a 5-slot Vago connector, I can use a much smaller 3-slot connector. I quickly realized that routing the cables over the top of the circuit board means they might get in the way of the case lid screws when trying to attach it. I also didn't want to interfere with the tiny Wi-Fi antenna too much. Therefore, I put most cables under the circuit board. Initially, I added a few supports below the circuit board to prevent it from bending, but those supports were now in the way of the wires. I just cut them off where they interfered with the wiring and reworked them later in CAD. Also, the board only had 3 mm of total clearance from the case at this point, so I needed to increase the distance for the next revision as well. Otherwise, the solder joints of the through-hole components might poke through the wire insulation when tightening the screws. The 2 cables going from the Vago connector to the relay inputs I left on top and tucked the longer one a bit behind the screw terminals. Inside the case, I used PVC insulated wire I still had lying around, which is a bit thinner overall. A word of caution with stranded wire: those Vago connectors with levers can and should take bare stranded wires. Don't use a ferrule. The ones with transparent plastic also make it very easy to see if the wire goes all the way to the end and if you removed enough insulation. For screw connectors, you always need to put on a ferrule to ensure a safe connection. Never screw in the bare strands. Apart from the ground clearance of the circuit board, I also didn't connect the bosses to the walls of the case. If you don't know what a boss is, like I did a few minutes ago, that's how you call the cylindrical protrusions used for screw connections and sometimes other stuff, which you'll see later. Anyway, I made all the mentioned changes, and since the prototype already works very well, I decided to directly print it in ABS. A tiny bit of warping occurred on the bottom, which is purely cosmetic. The inside dimensions are still spot on. With everything wired up, it was almost time for the first test run and a few temperature checks. Of course, we first need to flash the appropriate firmware. In reality, I did this right when the first controller arrived. Since I never worked with ESPHome before, I needed to make sure they work as intended. In case it's your first time as well, I'll give you a brief overview on how easy it is. This is by no means a tutorial on ESPHome though. You'll find those elsewhere. There are a few ways to go about this. The Home Assistant add-on ESPHome Builder will only allow flashing via HTTPS, so you need a domain and an SSL certificate for this to work. Therefore, flashing via the ESPHome website is the easiest way for most people. In any case, you need a browser supporting web serial for the initial flash. I used Google Chrome. Firefox does not work. Later on, you can just do updates over Wi-Fi. Controllers with a built-in USB port can be connected directly to the computer. For my specific board, there's no USB port, so we need to wire it up using an USB UART adapter. Since the ESP32 runs on 3.3 volts, the UART adapter needs to be set to 3.3 volts. Otherwise, you'll immediately fry your precious microcontroller. RX on the UART adapter needs to be connected to TX on the board and vice versa. Connect ground on both sides as well. Now this board is a bit special because it uses 5 volt to power itself. Since the UART adapter is set to 3.3 volts, you can't just use the VCC pin for the power or the controller will end up in a boot loop after flashing. Ask me how I know. So after figuring this out, I simply soldered a pin to 5 volt on the adapter and connected this one to the board instead of VCC. Flashing the firmware is pretty straightforward. You need to connect the UART adapter, hit Prepare for first use and wait a few minutes. After the initial flash, you need to configure Wi-Fi. By then, Home Assistant's ESPHome Builder add-on should have already discovered your newly flashed device. The controller locks everything it does to serial, so while it's still connected to your computer, you can have a look in here for troubleshooting. From here on, you can configure and update anything over the air. I took the configuration YAML directly from the ESPHome website and just pasted it in here. Notice that the new device has a section for Wi-Fi using the code word secret. This means it's taking the actual value from your secrets configuration, so you don't have to show your Wi-Fi password to the whole world when making videos. And also so you only have to change it in one location. When I initially tried flashing directly from the ESPHome Builder, I didn't know I needed to add the Wi-Fi section, so that's probably why my controller didn't work at first. The updated configuration needs to be flashed onto the controller. And after that, it should be ready to be added and controlled via the ESPHome integration. No cloud or internet connection required. Nice. So let's run this thing for a while and see how heated things will get. The relays both work as intended so far. No big deal though, it's just 5 wires after all. To my surprise, everything stays rather cool. No more than 50 degrees C on any part. Not even the screws or the sides of the heater get warmer, so there's no need to worry about my ABS parts. Apart from the almost 300 degrees of the heating element, the front of the heater goes up to 80 degrees. But even that would be fine for ABS. The roughly 2 amps in current difference between the low and high power circuit of the heater results in a 5-degree temperature difference on the relays when measuring with my infrared thermometer. Time to design the top part of the case. To have everything aligned perfectly, I used the same sketch as for the base. I also added a different grill pattern to the top lid, mainly because I like the look of it, but also for a bit of extra airflow and for those angry Wi-Fi pixies to pass through. For the screw holes bosses, I flared the base out a bit to have enough material left for the screw head recess. The first prototype did already fit flawlessly. It just had a bit too much play on the outside lid for my taste. Not that it mattered after screwing it tight, but I reduced it nonetheless. I printed the lid in PLA because it doesn't come into contact with heat anyway. I could replace it easily at any point, but I can already tell you there were no issues so far, even after hours of continuous use at full power. There was one last thing I wanted to add though. Since those heaters will be turned on and off fully automated, I wanted an easy way to tell if they were on and which heating element exactly. Years ago, I saw a video where somebody used transparent PETG filament to route light. So far, I never came around to actually apply that trick, but for this project it's a great addition. For the first attempt, I simply added holes and a few millimeters of material around them, hoping it's enough to guide the filament. Those relay LEDs are surrounded pretty closely by much taller parts, and I didn't want to have thin bosses breaking off easily. But I was never able to point the PETG perfectly straight onto the LED. There's way too much wiggling around involved, and the results showed vast differences in brightness. I ended up adding the thin bosses, and by flaring them out at the bottom, they worked pretty well and didn't break off too easily. While writing the video script, it occurred to me that I could have also added fins to the left and the right, since there are no other components in the way. So I did that even though I already printed all the lids I needed. Since I'm releasing the STLs, they are a great addition. Check out the link below. They are free, but you can also choose to leave me a tip to support my work. Or check out my other projects like Gatoino or my courses on 3D design and printing. Thanks for your support. As for the LEDs, I deliberately made the first 2 layers too tight for the PETG stick to poke through. This keeps it from falling out. After printing, I enlarged the opening a bit with a utility knife, so the spot is larger while still having enough friction left so the PETG doesn't move around. For maximum brightness, both ends need to be cut flat. The length ended up being exactly 22 mm, which makes the stick stay ever so slightly below the surface of the lid. The resulting brightness isn't exactly the same for all of them though. The LEDs themselves aren't always soldered on perfectly flat. But that's fine for me, they're still bright enough. Before I reassembled my prototype unit for good, I pulled out all the wires from the controller case to measure their length. After all, I still had to modify 3 more of them. Funny enough, they all ended up being pretty much exactly 15 centimeters long, except for the permanent live wire, which is 30 centimeters long. With those numbers, I could go ahead and do a small batch production of all cables in one go. This made wiring them up a breeze. Somewhere along the way, I also learned that those connectors aren't just hard to remove, but there's an actual safety latch you need to press through the shrink tube in order to release them easily. Just for fun, I also wired up a BMP 280 temperature sensor I got as a 5-pack for €2. It's already integrated into ESPHome, so getting it to work was just a matter of a few lines of configuration. Right now, I don't have plans to use it permanently, but maybe I'll design a small adapter board for it in the future. This would enable more sophisticated logic in Home Assistant to not just turn on the first heater in the list, but the one in the coldest room, for example. I've been using the heater for the last couple weeks while making this video and haven't had any issues so far. The Wi-Fi connection is way more reliable than I imagined, even though the signal strength is shown as rather weak. It's easily 10 times more reliable than my Zigbee switches. In case you also want to mod such a heater, follow the link in the description. In any case, I hope you enjoyed this in-depth project video and tell me what you had done differently in the comments. See you in the next one.